Okay, this is the second video on 2.6 looking at moments and center of mass. Center of mass of a planar lamina, so you can think of that as a closed region in the xy plane, a closed and bounded region in the xy plane. Can think of it as like a cardboard cutout, and then finding where on that cardboard cutout where you can rest that on a pencil tip, and that would be balanced. We're going to be looking for the center of mass of like a piece of cardboard. Now, mass is going to be your density times area. Density is mass per unit of area. We're going to let f and g be continuous functions on a closed interval ab, where f of x is greater than or equal to g of x on the closed interval ab. So we have an upper function, a lower function. Continuity implies we have an antiderivative. Let the region bounded by f of x and g of x have a uniform density of rho. Then the mass is going to be the density, rho, times the area, which is the integral from a to b of f of x minus g of x dx. And so we'll kind of give you an idea of where the moments about the x and the y-axis come from. So what we're going to do is we're going to partition the closed interval AB into n subintervals. Okay, so there is A, and then B, f of x, g of x. And we're looking at, here's our area right here. Then we'll draw a representative rectangle here. And the mass, and we can say this is like the ith rectangle in our partition. So the mass is going to be the density times the area. So the area, we'll go ahead and say that the area, the height is about f of xi minus g of xi, and then the width is about delta xi, where specifically x of I, y sub I is going to be the center of mass in the representative rectangle. So the xi would be dead center in the middle of the rectangle. So your xi would be somewhere right here, and the y sub I would be right in the middle there. Anyways, let's go ahead and continue. So the x of I, y sub I is the center of mass of the representative rectangle. Okay, so there it is. So there's the center of mass, and then the f of xi plus g of xi all over 2. That's just the average of the top and the bottom. So that's going to give us right in the middle. Okay, so the moment of this, about the x-axis of this ith rectangle, is going to be the mass times the distance of the center of mass of this rectangle to the axis, the x-axis here. So the mass is m sub I, and then the distance is going to be y sub I. So mass is rho times f of xi minus g of xi delta xi. So that's your density times the area, and then the y sub I is the distance to the x-axis. Okay, and then this ith rectangle here, the moment about the y-axis is going to be the mass times the distance. So m sub I, x sub I. Okay. So x of I times rho f of xi minus g of xi delta xi. Then what we'll do is we'll sum up all of these individuals and let n go to infinity. And that'll give us the following integrals for finding the moments about the x-axis and the y-axis. So the moment about the x-axis is going to be rho over 2, integral from a to b, and you had the f of x minus g of x times f of x plus g of x all over 2, so you got that f of x minus g of x times f of x plus g of x, so that's a difference of squares, so we can write that as f of x squared minus g of x squared dx. Okay. Moment about the y-axis, rho, integral from a to b, x times the f of x minus g of x dx. Your center of mass is going to be the x bar, y bar. Which is going to be the moment about the y-axis over m, comma, the moment about the x-axis all over m, where the mass is the density times the area, so rho integral a to b, f of x minus g of x dx. Okay, so we're going to do one example of finding the center of mass. So we're going to find the center of mass bounded by y equals 5x squared and y equals x squared plus 5. The first thing we're going to do after we finish writing this down is it's going to be of uniform density. We can say uniform density rho. And so the first thing we got to do is kind of have an idea of the region that we're looking at. So we're going to find the intersection of these two graphs. So where does 5x squared equal x squared plus 5? So it's going to be, where is 4x squared equal to 5? Divide by 4 and then take the square root. So x is going to be plus and minus the square root of 5 over 2. That's where they're going to intersect. Okay. And one of the parabolas, the vertex is at 0. The other one is at 5. And then if we plug in the square root of 5 over 2 plus or minus of that into either one of the formulas, we're going to get about 6.25. That's going to be the y-coordinate of intersection. So up here, that's the x squared plus 5, and then down below, that's the y equals 5x squared. So we have the region. So first order of business is we'll find the mass, and then maybe the center of mass is here. Maybe it's a little bit lower. But that's that point there. That's going to be where we can balance this object on a pencil tip. Okay. All right. So the mass is going to be the density times the area. Oh, we lost our negative sign here. Oops. Let's put our negative sign in there. All right. I might have undone it on accident. So here is the upper function minus the lower function. Now, because these are symmetric with the y-axis and we're uniform density, we can go ahead and cheat a little bit and say this is 2, and then we're just going to find the mass of the right-hand side twice because of the symmetry. Okay, so 2 rho, integral from 0 to square root of 5 over 2, and that's going to be negative 4x squared plus 5 dx. So it's going to be 2 rho. Negative 4/3 x cubed plus 5x, evaluated from 0 to the square root of 5 over 2. So 2 rho times negative 4/3 root 5 over 2 cubed plus 5 root 5 over 2. And then plug in the lower limit of 0 plus 0, so it doesn't do anything. So 2 rho times negative 20 root 5 over 24 plus 60 root 5 over 24. So get a common denominator. And so that's going to give us 80 rho root 5 over 24. And we'll reduce to be 10 rho root 5 over 3. And so that is going to be the mass. Okay. The moment about the x-axis is going to be rho over 2. Integral from negative root 5 over 2 to positive root 5 over 2. Okay, upper function squared minus the lower function squared, and then we're going to integrate with respect to x. Moment about the y-axis, rho times the integral from negative root 5 over 2 to positive root 5 over 2, x times the upper function minus the lower function, and integrating with respect to x. Okay, so we'll carry this on to the next slide here to finish up the integration. Okay, so there it is. So let's go ahead and work out the moment about the x-axis. Again, I'm going to go ahead and cheat and use the symmetry here. So for the moment about the x-axis. Okay. So we'll go ahead and FOIL the x squared plus 5. So it's going to give us x to the fourth plus 10x squared plus 25. And then minus the lower function of 5x squared, so minus 25x to the fourth dx. So that's going to be rho, and then if I integrate, I got x to the fourth minus 25x to the fourth, or minus 24x to the fourth. So that'd be negative 24x to the fifth over 5, plus 10 over 3 x cubed, plus 25x, and evaluated from 0 to the square root of 5 over 2. So it's going to be rho, negative 24 over 5 times the square root of 5 over 2 to the fifth, plus 10 over 3 square root of 5 over 2 cubed, plus 25 square root of 5 over 2. And then plugging in the lower limit of 0, we just get a bunch of zeros. Okay, so this is going to be negative 600 root 5 over 160 plus 50 root 5 over 24 plus 25 root 5 all over 2. The common denominator here is going to be 480, so I went ahead and did the calculations of getting them with a common denominator of 480. And so that's going to give us 5,200 rho root 5 all over 480. And then we could reduce, and that's going to give us 65 rho root 5 all over 6. Okay. We'll go ahead and calculate the moment about the y-axis. We'll find the center of mass, and then we'll kind of look at what this looks like on the graph. Okay, so a moment about the y-axis. There it is. And by symmetry, the moment about the y-axis is actually going to be 0 because it's going to be perfectly balanced left and right sides from the y-axis. So it's going to be rho, integral from negative root 5 to positive root 5, both of those over 2 respectively, negative 4x cubed plus 5x dx. So it's going to be rho, negative x to the fourth plus 5 over 2x squared, and evaluated from negative root 5 over 2 to positive root 5 over 2. And so what's going to happen is both plus and minus root 5 over 2 to the fourth power or to the second power is going to absorb the negative, and so you'll end up getting the same result. And so we're going to have whatever this value is, you're going to have the same value here minus the same value here, and so this is going to end up being 0. Okay, so 0. So on the next slide, we'll go ahead and find that center of mass. So moment about the y-axis is 0. Moment about the x-axis is 65 rho root 5 over 6. And then the mass of the system is 10 rho root 5 all over 3. The center of mass is going to be x bar, comma y bar. So x bar, comma y bar. So m sub y over m, comma m sub x over m. So it's going to be 0 over 10 rho root 5 over 3, comma 65 rho root 5 over 6, divided by 10 rho root 5 over 3. So that's going to be 0. Keep the top fraction and flip the bottom fraction over and change that operation from division to multiplication. And so that's going to simplify down to 0 and 13 over 4 as the center of mass. And I think I have on the next slide what that looks like graphically. Okay, so you can see the lower function, 5x squared in blue, the upper function in green, the y equals x squared plus 5, points of intersection, negative 1.118, and positive 1.118, that's on the x. The y values are 6.25, and the center of mass is 0 comma 13 over 4, which is 0 comma 13.25. And so if we took our pencil tip and placed it right where that point is there, it should balance. Okay, if we were able to cut it out on a piece of cardboard and we did a really good job, it would balance right there. And so that's the center of mass there. Okay, so I do have one more example that's going to be on the next video here. So that's going to be part 3 of 2.6. That's moments and center of mass. So we'll see you then.